Hello and welcome to my video, lesson 6.2, part A. So this is about permutations of distinct objects in factorial notation. So what we're going to do is we're going to consider the word perms. Now there's a big long description of what this question could look like right here, but I'm just going to talk it through as per normal. Okay, so we're talking about this word perms, and basically we're rearranging these letters into whatever order we want. Etc., etc., right? We're taking those same letters, those 5 letters, and we're rearranging them in different ways. So, considering our fundamental counting principle from the last video, what we can do is we can say, well, how many options do we have for the first letter? Well, we have 5 options, but once we choose one of those letters, we can't reuse it in the word. So now we have 4 options, and then 3, and then 2, and then 1. So we've basically seen this already with fundamental counting principle, but the point here is when you go 5 times 4 times 3 times 2 times 1, we have a special notation for this. This is called factorial notation. It's the exclamation mark. So what we say is this is 5 factorial. So this is helpful because it allows us to simplify things and do questions a little faster. Let's go ahead and take a look here. When in a fraction, we can simplify by unzipping the factorial. So what we can do is we can solve these questions much more easily because we know how to unzip. So what does that mean? Well, we leave the smaller factorial there, and then we unzip, meaning we take apart the bigger factorial until we get to the point where both factorials are the same. Now we can cancel those two, and so we're left with 10 times 9 times 8, which is 72 times 10, or 720. So much, much easier to do because we're able to unzip the factorial. Otherwise, these numbers are too big. In fact, we can do numbers like 73 factorial over 71 factorial, but our calculator would actually have an error if you tried to do this in your calculator. But we can do it because we know how to unzip this. So I'll just go ahead and quickly show this, right? Whereas I'm going to pull up the calculator now. Actually, I'm going to just move this over. So if we tried to type this in our calculator, we would type in 73. The factorial button is math over to probability down to number 4. Okay, and then if we put in 71 over to math probability number 4, and we press enter, you can see it's error overflow. Why is that? Because the number for 73 factorial is too big. It's too big for our calculator to handle, right? If we had like 65, it might work. But you can see it's times 10 to the 90, so it's already quite large. So maybe 68, maybe 71, or 70 works. 70 does not work. So what you can see here is our calculator is too dumb to actually solve this question. So we are smarter than our calculator because we can simplify it, and we can get an answer of 5,256. So the point is that some numbers are too large, and we can do it because we can unzip. So this is important to be able to do. So we're going to keep going now and keep unzipping. Not only is it important for numbers, but it will be important for algebra in a moment. So go ahead and try this example. Pause the video now and see if you can solve it. Okay, so the point that you're going to do is you're going to put the smaller number down, smaller factorial down, and then you're going to take the larger factorial and start breaking it apart until you get equal to the smaller factorial. So the 5 factorials are going to cancel. And now we're going to have 9 times 8 times 6, 7 times 6, and we get 3024. Okay, so it's the same rules here with numbers as with algebra. If you can do it with the number, you can do it with the letter. That's my rule. So let's go ahead and do this. We're going to take the smaller factorial, and we're going to just write it down. N minus 1 is smaller than n because it's minus 1, right? So now we can start unzipping the n. And what does that look like? Well, every time we do a factorial right here, let's use a different color. But every time we do a factorial, like 9 is then times by 9 minus 1, right? That's 8. And then to get 7, it's 9 minus 2 that gets 7. And then it's 9 minus 3, etc. So the point is that a factorial is always going to fit this sort of pattern. All the way until you get to the number 1. Okay, so that's what a factorial is. So we can just unzip it like I did in red here. And then hopefully you can see that the n minus 1s cancel, and this simplifies to just n. Okay, pause the video now and try the next example on your own. Okay, let's go ahead and try this. So we're going to write down the smaller factorial. Which one's smaller? Well, n minus 3 is smaller than n minus 1. So you start by writing the smaller one. Then we unzip the bigger one until they look the same. Now that they look the same, we can cancel out those two parts, and we're left with n minus 1, n minus 2. And you could multiply that out, and we get that. I think either way is fine. I'm going to accept either answer. Okay, let's keep going here. Let's try to algebraically solve this question. If you pause the video now, you can try it yourself. Okay, to algebraically solve, we really don't want those factorials because we don't really know what n is, so we don't know what to factorial until. So what we need to do is cancel out by unzipping. So what we're going to do is we're going to write down the smaller number. So n minus 2 is smaller than n. Then we're going to start unzipping the n until it looks the same as the n minus 2. From there, we can cancel out the two parts that look the same. We can multiply the n into the brackets. Now we can move that 30 over. And so we have minus 6 and plus 5 equals 0. You're going to notice here that if this is true, we could say n equals negative 5 or positive 6. However, n only equals the positive version. Why is that? Because if we have, we cannot have a factorial of a negative number. I'll go ahead and, it's not really a proof, but, I'll go ahead and show you by trying this in my calculator. And you can see that it tells you you cannot have a value in this function, right? So you cannot have a negative inside a factorial. So it's n equals 6 because this one is not allowed. Okay. Let's keep going with a couple different examples. So determine the number of permutations of each word. We have the word phone here. And every item in the list is unique. And so there you go. And we've got number afterwards, but we'll try phone first, and then you guys can try the other one. So if all of the different items are unique, well, then it's just going to be 5, 4, 3, 2, 1, which I wouldn't bother writing out anymore. It's just 5 factorial. But it is, you can use fundamental counting principle because fundamental counting principle is the same thing as a permutation. Okay, if we go ahead and try the next one, then it would be, just 6, 5, 4, 3, 2, 1, or 6 factorial. I believe this is 120 and this one's 720. Yeah. Okay, so the permutation formula is written in your formula sheet, but it's right here. We call it NPR or N-perm R. And so what this is it's saying the total number of items and then the number of choices from the item. And if it's permutation, then order matters. Okay, so here there are, there's a question about 8 swimmers. How many different ways can these 8 swimmers get gold, silver, and bronze medals? Well, there's 8 swimmers, which means that there are 8 people to choose for gold. Then once you've chosen one, 7 people, then 6 people. Right? So we could just do it with fundamental counting principle, but we could also do it with perms. So how would this look with a perm? So it would be 8 perm 3. Okay, so there's 8 swimmers we can choose from and 3 different positions that we're choosing for. Now, if we use the formula, it's 8 factorial over 8 minus 3 factorial. Well, what does that actually mean? It's 8 factorial over 5 factorial. Well, what does that actually mean? Well, it's 8 times 7 times 6 times 5 factorial over 5 factorial. Well, that means the 5 factorials can cancel. And would you look at that? It's back to the 8, 7, 6 value that we had before. So 336. So perms are just the same thing as fundamental counting principles. So use whichever one makes more sense given the context of the question. I am going to change this though. How many permutations, how many 3-letter permutations of the letters in the word blank? No, I'm going to go 4-letter. Okay, so for this one here, same sort of thing. Now, you're going to notice there are 5 choices, so 5 perm 4. So we're choosing 4 of them out of those 5 choices. which we could go ahead and, write down as a perm statement if you'd like. So it's 5 factorial over 1 factorial, which really means it's just 5 factorial or 120. But what if we make a restriction? So what if B and K must be in the first and last position in either order? So now it's 1, 2, 3, 4 options, but there's only 2 options for the first position, B or K, and then once we've chosen one, there's only 1 option for the last position. Then inside of that, we have the other options. So there are 3 other letters, and then we can go 2, and since we're only using 4-letter permutations, we can end there and get 12. Okay, what if BLA must be together in the new word? And let's just say, let's go back to a 5-letter word. Okay, so pause the video now and see if you can figure this out. Okay, if BLA must be together, what I like to do is I like to set this up as one item and then NK as the last part of the item. So there are 3 different characters. This counts as 1, this counts as 1, this counts as 1. There are 3 different characters that we can rearrange. So it's 3, 2, 1. But BLA can be rearranged to LALB or whatever else, i.e. it can be rearranged also 3, 2, 1. So I like to write this like this. I like to show it kind of like this. And so we have 6 times 6, 36 as our final answer. Okay, we're almost at the end. Here is the second last question. When setting up for a team photo, the coach wants to make sure that 2 friends are together and the goalie is centered in the shot. If the team consists of 9 athletes, then how many different ways can the team be arranged? So I recommend this one would be a good question just for fundamental counting principle with the goalie in the middle. Now, the goalie has to be in the middle, so that one's locked in. So now how many athletes do we have to choose from? 8. But 2 of the friends must be together. So what we're going to do is we're going to lock down these 2. Actually, I'm going to go like this. I'm going to lock down these 2, and I'm going to consider this as one item. So now how many different items do we have? Well, we have 7. So this is 7, 6, 5, 4, 3, 2, 1. But the friends can also be rearranged in either order, so it's 2, 1. This is kind of how I like to do these grouping questions. Whenever it says grouping 2 friends, 2 cars, 2 whatever, I like to build it like this and consider this as one item. Okay, so this ends up being 7 factorial times 2 times 1, but who cares? So this is 10,080. Okay, last question for the video for this topic. Solve for n. So this question just has a general perm. And so what we need to do is build this out. So it looks like this. And now we have to simplify the perm. So this is 72 over here. we're going to write down whichever, or simplify the factorial. So we're going to write down whichever one is the smaller factorial, and then we're going to unzip the larger factorial until they match. Then we can cancel out the matching parts, and we can multiply that out. Okay, and then we can move the 72 over. And now we can have n minus 9, n plus 8. And so n equals negative 8, comma 9. And because we cannot have a negative total number of items, that's kind of where the perm is coming from, right? Slash, we can't have a factorial with a negative. Then n equals 9 is our final answer. All right. I hope this video helps you better understand perms with distinct objects, and usually no repeating, and what factorial notation looks like. Hope the video helped, and good luck.